Okay, welcome back. This is now then 1.6 and appropriate because last time we just dealt with inverse functions. Now we're dealing with two functions that are inverses of each other, the exponential and the logarithm. We want to go through all their properties and hopefully remind you of all the great things going on there. So first, a review of properties of exponents. Seems like every time I used to have to take a new math class, I'd have to go through and review all these properties. They're super important, but they're kind of easy to mess up if you don't work with them every day. Anyways, anything to the 0th power except 0 is equal to 1. If you're multiplying two exponential expressions with the same base, are you adding or are you multiplying the exponents, right? That's always the question. It's you're adding. So x to the y. And we could just do these in sort of examples, like 3 to the negative x times 3 to the positive x is equal to what? Well, it's 3 to the negative x plus x, which is equal to 3 to the 0, which is equal to 1, right? I forget what they call this rule, but it looks something like this. You have 2a cubed b, and then you raise it to a power out here, maybe the 4th. Essentially, it works kind of like a distribution. You'll then have 2 to the 4th, a to the 12th, b to the 4th, 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 16, a to the 12th, b to the 4th. That's what else? I don't know. Quotient rules. 3a cubed b to the 4th all over 6a b to the 5th. So remember, you want to avoid negative exponents. So anyways, 3 over 6, first off, that's just 1 over 2. And then I'm going to move the a up. So it'd be a to the 3 minus 1. So I'll have 1a to the 3 minus 1 is 2. And then I move the b down, right? So I want b to the 5 minus 4. In other words, b to the 1, which is just b. So it's a difference rule, really. So in general, they could write that as x to the a all over x to the b is equal to x to the a minus b, or it's equal to 1 all over x to the b minus a. So in general, that's kind of what's going on there. Any other rules? Sure. Quotients to powers. So let's say negative 2x cubed y all over, I don't know, 3xz squared raised to the negative 1 power, right? Or let's make it more interesting, negative 2 power. So the first thing you want to probably do is get rid of that negative, so it completely flip the entire thing. That's one way to go about it. 3xz squared all over negative 2x cubed y, and now it will be positive 2 on the outside. Then it's kind of just a matter of distributing the 2. When you do that, make sure you keep this guy kind of in parentheses, because the exponent will affect the negative sign on the 2. So end up with 3 squared is 9, x squared, and then z to the 4th. All over negative 2 squared is 4, and then x cubed squared, that'll be x to the 6, and then y squared. Okay. I'm not done yet, because I can't have repeated bases floating about, so I need to reduce that portion of it. So it seems like my camera's tilted weird. All right, sorry, I hope that doesn't bother anyone. That's better. So I got 9z to the 4th. I'm bringing the x down to avoid negatives. All over 4x to the 6 minus 2 is 4, and then y squared. That should do it. So good stuff. One thing that is kind of important later on for us will be rational exponents. So this is problem 1 from the book, part A. We got 25 to the 3 halves. I mean, you can put that in your calculator, but if you these expressions are going to result in some of our calculations, so it's sometimes quicker just to do it in your head and not be overwhelmed. So how did that work? Well, you're going to sort of split up that fraction using power rules, I guess. 25 to the 1/2 then is just 5, because the 1/2 power is ultimately the same as saying square root. So you have 25 to 1/2 is 5, and then you cube that, and that's 125. So just, that's in your future. Hopefully you took your basic algebra classes seriously. Anyways, sketching exponentials. All right, so for these guys, pretty simple. There's 2 versions. Obviously, on top of that, then all the translated versions, but just the general ones, we have y equals a to the x. Here, a is assumed to be greater than 1. And then over here, y equals a to the x, where a is in between 0 and 1. Okay. The first guy is the exponential growth. The second guy is the exponential decay. And these functions are 1-to-1, which is awesome. The domain, so some technical details here, I guess. The domain, -infinity to infinity. The range is going to go from 0 to infinity. There is kind of a horizontal asymptote at y equals 0. 3 SE at y equals 0. There's a y-intercept at 0, 1. I think that's about all the information we need. These are 1-to-1 functions, so they're invertible. Obviously, we'll get to that. Okay, so that's the main picture here. Let's go through and try to maybe graph 1 or 2. This is problem 26. Wants to view the graph y equals 3 to the x minus 1. Okay. So one approach is to graph y equals 3 to the x. Okay. So y equals 3 to the x, x and y here. So -2, -1, 0, 1, 2. 3 to the -2 is 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. And then we have 9. Graph that junk. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. -2, 1/9. 1/3. 1, 1/3. 2/9. All right, so this will be sort of start. Then just use translations to get your new graph. So when you go x, the insides, and you're subtracting 1, it's just a matter of shifting to the right by 1. So you just take all these points and move them over. Okay, and that will give us sort of the official version that we were after, 3 to the x minus 1 here. Okay. All right. Maybe some more important ones, like 29. This guy comes up probably in probability theory, I assume. I don't know. I wouldn't recommend doing this by shifting or anything. I wouldn't even know how. You probably just have to do a table of values. But if you do go through the table of values, it's pretty neat. It's a bell-shaped curve, which is why I'm saying it's probably used in probability and stuff like that. One of the things we'll learn how to do here in calculus classes is to figure out the area underneath these curves. And you may have had to do that if you took statistics or something, presuming that the area underneath this curve is equal to 1. I don't think it is, but it's kind of related to that idea. You know, you're looking for the probability of being in between these two values, and you could kind of do that by figuring out the area underneath this curve, all that jazz. So if you get a chance, take stats and see how this stuff's related. Anyways, section 3 then, we get into the actual logarithm. In particular, we're going to be concerned with the natural logarithm with base e. Before we were dealing with general bases, but now we want to use base e. Okay. Alrighty then. So, you know, before in your intro classes, you had log base b would be the inverse of b to the x. And we probably defined it, you know, y equals log base b of x if and only if b to the y equals x. Now we want the base to be e, so we'll say, you know, y equals log base e of x if and only if e to the y equals x. Okay. In particular, though, we're going to rewrite this expression and using the symbol ln of x. Okay, so when you see this, just assume it's a logarithm with base e, and its inverse function is e to the x. Okay, okay, so first off, what does this thing look like? And what we'll do is just a matter of rotating it about the line y equals x. So first graph y equals e to the x, which is just an exponential growth function. It looks like this. Okay. So to get our graph of the logarithm, rotate it about this diagonal. Okay. So for the logarithm, it'll look like this. Okay. So this will be y equals ln x, and this other guy was y equals e to the x. Okay. So the characteristics of the natural log will kind of be opposite to the characteristics of the exponential. First off, its domain is the range of the exponential. It's from 0 to infinity. The range then is from negative infinity to infinity. It has an asymptote, a vertical asymptote at x equals 0. The a at x equals 0. What else? It has x-intercept now, this time, at 1, 0. Obviously, it's 1 to 1 again. And I don't know what else to say about it, really. So let's move on. Okay, so other properties of logs then. Look at section 5. These are the more algebraic properties that we'll use to simplify logs. Stupid camera thing. Back in line. Okay, that's a little better. So the properties of logs, these are the, you know, the standard ones. I'm going to remark this now. Where I can go without going off the camera. So the product rule, first, if you have the ln of x times y, that's equal to the ln of x plus the ln of y. And there's restrictions on these events, especially you can't put anything that's less than or equal to 0 in a natural log. So That's a big issue, a big no-no. Anyways, the quotient ln of x over y is equal to ln of x minus ln y. Okay. Then the power rule, ln of, let's say, x to the z is equal to z ln x. And there's always two versions of these, expanding and then condensing. So it's like expanding. So 13. We have the ln of x times the square root of x squared plus 5. I want to expand this thing, so write it as a sum of logs. So here we go. Things are really screwed up. It's like the more I mess with the thing, the worse it gets. Just stop touching it. All right, so anyways, first use the product rule, so ln of x plus the ln. And on top of that, I know that the square root can be rewritten as a fractional exponent. So I'd have x squared plus 5 to the 1/2. So I'm going to bring the 1/2 out in front of the ln. I'll have 1/2 ln of x squared plus 5. And that'll do it. Okay, that'll be all I can do. Let's look at the other version, condensing. We got, what the heck is this? Oh, this was 93. This will be 103. So 1/3 times 2 times the ln of x plus 3 plus the ln of x minus the ln of x squared minus 1. I'm gonna just condense the inside first. To condense it, I can't have a constant in front of the log, so I'm gonna rewrite that as ln of x plus 3 squared plus the ln of x minus ln of x squared minus 1. Okay. Then I'm going to combine these guys. So I'll have 1/3 times the ln of x plus 3 squared times x and then you can combine these two by making a fraction. So 1/3 times the ln of x times x plus 3 squared all over x squared minus 1. And then take the 1/3 and pull it inside as the exponent, and it will be a cube root. So the ln of the cube root of x times x plus 3 squared all over x squared minus 1. Okay. Okay. So we'll want to be solving these things. We'll be working with solving these things later on. In Calc 2 a lot. So let's take a look at it. So first, the cancellation equations are helpful. So it's just kind of a reminder here. And it's from compositions, right? So if you have a natural log and you put inside of it the inverse, e to the x, you'll end up with x. And in general, that will be true for anything you put in the exponent. So if in the exponent you put sine x, the answer here, the reduced version then will be sine x. Likewise then, if you have an exponential and you put a natural log in its exponent, you'll end up with just x. So likewise, if you put anything inside of the natural log, let's say x squared plus 1, you'll end up with that popping out at the end. All right, so we want to be able to solve these things. Let's just look at two. Two or three of them. First, exponential type equations. Let's say 3e to the x plus 2 equals, I don't know, 23, right? So first you want to isolate e to the x. So move the 2 to the other side. I get 21 over there. Divide both sides by 3. E to the x is 7. And then take the logarithm of both sides. And on this side, you see you have that composition thing going on. So ln of e to the x is just x. Ln of e to the x is just x. And then over there, you're stuck with the ln of 7. You get an approximation for it or whatever. Let's take a look at another example. Ln of 2x minus 3 minus the ln of x equals 10. So in this case, you want to take advantage of the definition of the natural log. So first I'll do quotient rule. So ln of 2x minus 3 all over x. And then on the other side I have 10. So using the definition, it's e to the 10 equals all this mess. So 2x minus 3 all over x equals e to the 10. And then we could solve for x. So 2x minus 3 equals x e to the 10. And then 2x minus x e to the 10 equals 3. And then factor out the x, you get 2 minus e to the 10 equals 3. Divide both sides by 2 minus e to the 10. And then hope that's the answer, right? The problem with these is, in general, you're going to have to plug them back into the original equation to see if they actually work. And so you would have to go over here and take a look at ln of 2 times this thing minus 3 minus ln of that thing equals 10. And just looking at this thing, you can kind of tell it's a negative value, right? You can see the 10 is really big, and 2 minus something really big will be negative, and then a positive over a negative will be negative. Okay? So this thing is less than 0, and then when you take it and you put it into here, you're going to have big trouble. Something less than 0 isn't going to pan out when you put it into a natural log. So the solution here is that there are no solutions. And the moral of the story is you have to check your solutions when you're dealing with logarithmic equations. Okay, thanks, bye.